So the focus would be on the definitions that we use to input the various parameters from the code to the program for the analysis. So I've shown here four stages here. One is the modeling part, which I assume that you all have done, and then we are looking into the modal inputs. So that will happen under the definitions, and then we have the analysis and then the responses to review. And in that specifically, for the code checks, we have outputs via the table as well as the graphical user interface. All right. Next, for the modeling and analysis, for the IS 1893 code, we have to specify the moment of inertia for the structural analysis for the members, specifically for the walls, beams, and columns. And that is given in the clause. I have shared the snippet here. So for columns, 70%, and then for beams, 35%. And for walls, we can assume, as in general practice, 70% or 80%, similar to columns. And for slabs, so for the flat slab system that are subject to out of plane deformations, then for that we can specify 25%, which are generally used. So this is available in ETABS through the property modifiers option. So I will try to connect these with the features in the ETABS, and then we will see a few models as an example to show the same. All right. Now the property modifiers are available in two locations to define. One is in the frame definition itself, or the section property definition itself, or beams, columns, walls, and slabs, where you can specify the modifiers directly. The other one is selecting the objects after the modeling and applying it as an external assignment to the members. So the first one is to have it permanent. Whenever you use that property, this property modifiers comes along wherever you model it. The other one is to replace the property modifiers if needed, or only you want to assign it to select members of the structure. So these two options are available to specify the stiffness properties for the analysis. And then you have to decide on the diaphragm type, whether it is a rigid or semi-rigid, or in other words, it is also called the flexible diaphragm in the code. So we have to check this after the modeling, a first analysis, to identify this. Right. But the general assumption is that for concrete slabs, it is unlikely that the slab will have large in-plane deformations. Exceptions would be for large openings in the buildings, or lengthy buildings where the stiffness is distributed such that some portion of the building, for example, the image shown here, which is going out of plane in the middle part of the building, then you will get the ratio greater than 1.2, and you will have to use the flexible or the semi-rigid diaphragm. And the types of analysis recommended in the code are the standard equivalent static method and then dynamic analysis. And in dynamic analysis, we have response spectrum, modal time history, as well as the time history analysis with nonlinear properties. So all of these are available in ETABS. But in today's discussion, we will restrict ourselves to equivalent static and the response spectrum method. So the equivalent static method, it is automated in the program. So that's why I have written on those clauses available in ETABS for your quick understanding. So this is already available to you. We will see those in the model. The other one is how the base shear is calculated, same as the code. You can see VB equal to AH into W. Now W is the seismic weight, which we will define through the mass source, which is a dedicated definition for any seismic analysis, whether it is linear static, response spectrum, or time history analysis. Program can select the mass source that you define. So the seismic weight for the structure will also be obtained with the definition. And the base shear will be distributed as per the quadratic distribution suggested in the code. For the linear static analysis, you have this available in the ETABS. And then in the spectrum, we have two types of spectrum. One is for the equivalent static method, the top one, and the other one is for the response spectrum. The key difference is that the time period, when it is small for the equivalent static, you'll have to take the maximum or the peak, let's say by G value. But for the response spectrum, it will be slightly different. It will start from a lower value of 1. So these two are also incorporated in the program. And then in the base shear calculation, it also applies the minimum percentage of base shear. Program will use this to apply the minimum base shear. So all the loadings required for the horizontal shaking is available in the program to you. You can simply start defining and using it. Yeah. On the analysis types, so these are the major definitions that we are going to deal with the program to input. The first one is the mass source, and then from the mass source, you will be defining the equivalent static, and in that we will be specifying the time period. So time period can be an user input using the empirical formula given in the code. Or you can ask the program to calculate the time period based on your model. That would be based on a modal analysis. So program will use the respective time period for that direction, which has the maximum participation factor. So that's how it identifies the time period for the building. The other option is a quick way of specifying the coefficient, which is 0.075 h to the power 0.75. This constant value 0.075 or 0.085 can be specified. Program can also use the height from the building and calculate the time period. So 3 ways of inputting the time periods. And then factors and coefficients are directly from the code. Importance factor, Z value, and R value. So the lateral loads can be applied as the auto lateral load, which we are discussing so far, and it also allows you the user to assign it as a user load. So if you have calculated the loads externally following a different guideline and you want to input that, then you can use the user lateral load. To apply the user lateral load, you will have to have the diaphragm assignments on the floors. So this will expose the diaphragms in the building, and you can specify the load directly in the FX, FY, and MZ for any twisting moment. Next, for the spectrum analysis, we have the modal analysis based on eigen or Ritz modes, and then spectrum functions we'll have to define, and the spectrum load cases. So in that we have horizontal component as well as the vertical component. We will discuss them both shortly in detail. And then we have the input for the design eccentricity. So this is not automated, but available in the program for the user to specify, because this will require the calculation of the eccentricity externally, and then you can assign it in the eccentricity input as an override or a constant ratio. Both are available to the user. Important thing to note here is the inherent eccentricity, that is the difference between the center of mass and center of rigidity, is already available. We need to exclude that and specify the calculated value. Now for the definitions, we have the mass source we're talking about. Now at this point, I would like to open the ETABS. I have a sample model where I can explain this quickly. Since all the inputs related to the 1893 are automated, we'll find everything under the definitions. So it is the definition. First thing would be the mass source. And we have the mass source. We'll have the default mass source, and then you can modify it as needed. Default mass source by the program would be the element self mass and any additional mass specified. But typically we'll follow the 1893 code where the load patterns or the dead loads and live load ratios are given. That can be specified directly here. And this can be applied as lumped mass to the stories, or can uncheck this in case your modeling is having masses at the levels between two stories. Then you can uncheck it to consider the mass in that level, or else it can be lumped at the story levels. Typically for most buildings this should do. For industrial buildings, make sure you uncheck this, as we expect many mezzanine and intermediate level loadings. And then by default lateral mass is enabled, that is UX and UI, and then the vertical mass, if specified, will be enabled. So if you're considering the vertical excitation, you have to enable this to have that. So that will be the mass source definition. And then for the linear static, we have the load pattern definition. I have defined it using auto lateral load specified to this code 1893. And then once you have specified and added to the list here, then you can modify this lateral load to specify other inputs, specifically the direction and eccentricity if needed in the positive, and then in the negative and enable. Actually, the program allows you to specify one seismic load pattern including all of these. You can enable all 6 and you can perform the analysis. In that case, program will generate sub-load cases for each of this. So it will be 6. You'll get 6 step outputs. But the convention is to have a simpler output for specific direction and eccentricity. So you can define multiple patterns and get the output as a separate output for each load case. So in this case, I'm keeping it with X direction without any eccentricity, and you have the story range as R value, Z, soil type, and importance factor. And the time period you can specify like this. It's an approximate, a quick one, or you can always use the user defined to give that value. In this example, I'm using the approximate 0.075 times the height to the power of 0.75. Same goes for the other orthogonal direction in the y. That's the definition. And that's all we needed in the definition part for a linear static analysis. Now, depending on the various clauses, you might need a response spectrum analysis or the dynamic analysis in general. You'll have to define. Again, we have to come back to the define. Mass source is already defined. The next item, let's take the response spectrum analysis. And we have the functions as response spectrum function to define. And we'll have a list of spectrum available. You can select it from here. You can see IS 1893-2016. And if you press add new function, you can get the default. You can name it 1/5. And suffixing with H for horizontal. Then we can specify the zone, I, soil type, and R values. So the spectrum will get updated for these values. It should be noted that it is a normalized function for the G. And this will be used under the load case definition for the spectrum cases. So under the spectrum, under the load cases, we have a modal case. We need it for the spectrum case to use. So we will check the default modal case by pressing modify show, and we have the type and select between eigen or Ritz. And depending on your P delta settings, that will come. So P delta will be discussed in a different session. So today's discussion will be more on the definition of the load cases using 1893. So the number of modes, the maximum number of modes that you'll specify, you can start with, as a thumb rule, you can take 3 per story that are translational in X and Y, and then a rotation about the vertical axis of the building is about the Z axis. So 3 modes will be the structural modes expected in a story. So multiplied by number of stories. We have 1, 2, 3, 4, 4 into 3, 12. 12 should be a good starting number. And we will review the model results to ensure the model mass participation is 90% minimum as per the code. So we review it and then come back and update it if needed. There might be cases where you will find a lot of local modes because of the masses or lesser stiff members model in the structure dominating in the initial modes. So we will have to address them on that. Those are the things that you deal with in your iterations of analysis to finalize the stiffness in the model. Okay, this is the model case definition, and we will define a new load case. Just load case that is called spectrum X direction, and then the case type would be response spectrum, and mass source is picked automatically. The loads applied would be acceleration load in U1, which is the translation in X direction, and the function would be 1893H, and the scale factor would be the G value. This will be our initial scale factor. This may be required to be enhanced if the static equivalent static base shear is more than the dynamic as per the code. So we will also have to do that. And then under the other parameters, you have the model case. We have only one model case, so it is automatically got selected. And the model combination method we specify. C case is default. I think it should be fine for most cases. Then the SRSS could be conservative. And the directional combination is needed when you are including the other direction loading as well. For example, in the U2 direction, which is the Y direction, here like 30%, then you can include it here, and then the SRS will kick in. And the model damping would be 5% of critical damping by default. You can specify it under the modify show in case you want to specify a different model damping. And then there is an option to consider the eccentricity. Note both for static as well as the response spectrum, you need to have the diaphragm. And we recommend a rigid diaphragm for this to assign the diaphragm eccentricity. Semi-rigid diaphragm will also can take the diaphragm eccentricity. Here you can specify as a ratio or specific to diaphragms at different story levels. That also can be specified here. That will be included. Same definition for the Y direction. You can quickly make a copy of it, except for the load name, which will be U2, and we will have this two cases. So these are the definitions for the static and the spectrum cases. Next one is the vertical shaking. So the code is guiding you when to consider the vertical shaking. So in zone 4 and 5, it is mandatory to consider. And in other cases, such as plan or vertical irregularities, then you'll have to consider this: soft soil, large spans, pre-stressed, large overhangs. So in considering all this, we'll have to specify the vertical shaking and how to specify it in the program. We have you'll have to define it as a user-defined spectrum. To do this, I'm going to show you in the model. You can see here again, you have to go back to the functions under the definition, response spectrum. And you can find for user, you will add a new function, alias 1893 V, and the damping ratio is 5%. Then the periods. So basically what we are trying to do here is to define this vertical acceleration. So as per the code, you have this formula given, which is going to be a constant function. There is no variation with the time period, so it is a constant function, and that's what I'm going to define now. Now you have this definition. So 0 And the value of the spectrum can be calculated from the constant formula given there. So can calculate as including all the factors and coefficients, 0 to 10 seconds constant. We'll see a constant line here. That would be the definition. Next, we'll define a response spectrum case. Make a copy of this case and we'll rename it. Now the load name would be U3 and the function would be 1893 V. The initial scale factor, we leave it to the G. Later, when the scaling or the enhancement to these static and dynamic Bayesian in the lateral direction, the same scale has to be used as per the code that we will update later. So that is the case. Rest of the definitions remain the same. Now we have 3 cases. Right. That's what you see in the slide as well. Next, the responses, which you will see that in the model itself. You can go ahead and run the analysis. Note there are no further assignment to the members directly, so everything is automated. Now you'll get to see the deformation specifically. So in the GUI, one of the window, you can turn it to the displacement. So it's automatically happening after the analysis. You can see this is for the first load case in the list of cases. We'll have to change to the lateral. Start with the static. So we have certain outputs in the GUI, which would be quite useful. So this is the unfactored earthquake in X direction. This is for the linear static case. We also have the spectrum cases. Let's start with the static and the deformations. You can run the mouse over the joints and read the values directly. Right click and get it in the form in detail, and then you have this particular output called story response plots. So here under the display type, you have various outputs. For example, autolateral loads to diaphragms or stories. Let's take the stories and you can check EQX and EQY. Loads are basically you're seeing the distribution, quadratic distribution. Applied to the structure. The same can be seen on the model as a joint load. So we have the diaphragm. Sorry, I haven't assigned the diaphragm. So it is directly to the joints, it is distributed. This is for the X direction, this is for the Y direction. When diaphragms are modeled, it will be assigned to the diaphragm's center, which would be the center of mass. Right. So we have maximum story displacements. can interact with the plot, read the values, or get it in a tabular form as earlier. The specific outputs that would be one is the displacement, other one is the drifts. You can see the drifts. So drifts are under control because of this stiffer walls present in this model. Then you have other outputs. Let me come back to this. So we're ensuring that drift limitation is under control or not. If so, as per the clauses, various clauses, and then we'll also have to do the scaling of the base shear. Story shears, can read it directly here under 714. For spectrum, so 530. Now can enter into the table output from the GUI, where we'll get various outputs. We'll come to this particular output, which is structure output, which is the base reaction. This is to compare the total base shears of static and dynamic. Make sure the cases are selected. You can exclude the model and see them. So you can see the FX for the EQX and the spectrum, and then FY for the EQY and SpecY. Now this ratio has to be taken out for feeding it in the scale factor of the load cases. So the first one has a ratio of 1.347, second one is having 1.317. And you also see the Z direction, vertical excitation. Now we'll have to scale the spectrum cases for this. So to this existing, without unlocking the model, you can do this. So analysis results will be lost for these modified cases. That's okay. We are going to rerun the load cases for the updated value. So this one will be multiplied by 1.347. This one will be multiplied by, you can do small calculation by specifying the expression here in the field itself. This is 1.317. And for the Z direction, we'll use the maximum of these two ratios, 0.37. Yes, those results will be lost. And then we'll have to simply run the analysis. You can see other cases are intact except for the spectrum cases. We run this. And go back to check same output. You'll see the scaling has been done. Now we'll have to check the irregularities clauses. So how we can check this? Now these are also available in the program. I will show you. So the code clause is typed here just for quick reviewing. Basically, we are going to compare the minimum and maximum and get the average. For this, I have a different model because first example was very symmetric building. So this building is more a realistic building that you'd be encountering mostly. So it has, yeah, this is complete. I can access the results. Now I can go to the show tables and I can go to the joint output under the analysis. So this is for the torsion, right? So go to the displacements and you have the option story max over average displacement. You can filter the combos and faces so that you have only those relevant. And we'll use the linear static case results because the spectrums will have lost the correspondence, so it is not useful. So use EQX and EQI for this output. So in the table, it will allow you to query, sort. So you can see tables. So I have, just to save some time, I've created this. Okay. So you can see the maximum to the average ratio is already there. You can directly get it from here. If you want to do some more calculation, you can use the help of Excel always. So all of this you can see for the EQX, these are under control or less than 1.4. You say maximum is 1.3, right? So you have this check can be done easily with the available output. So there are other plan irregularities, such as re-entrant corners based on the plan dimension ratios, which can be done by the designer. There is no need to check, but if you want to model such things, like you have the L-shaped building or T-shape or this kind of cruciform, then what we expect is the re-entrant corners. So one thing should be kept on the mind is that you should not use the rigid diaphragm initially to know any concentration of stress happening at this re-entrant corners. So you have to check for both cases always. So without diaphragm first, and then decide on the diaphragm to have the, to consider both the severe effects and use the one. Similarly, for the cutouts, you can decide, think if the cutouts are inside the building, then it is 50% and above, then you can consider it as irregular. And then out of plane offsets of vertical elements, think We generally avoid this, but in such cases, you know this beforehand, so we'll have to consider different types of advanced analysis to model such things, not to rely on simple linear static cases. And then non-parallel lateral force system. This is a quite common one when your lateral resting systems are not aligned with the global X and Y, then that is also irregularity. But in such cases, the design is taking care of that thing by considering the 30% of the other direction force in the considered direction for the design. So this is one way to consider it. But if you want to model them, then please use the dynamic analysis to capture those effects more accurately. And then we have the vertical irregularities, which is checking the stiffness, which is already available in the program. So for the soft story, you can get the output under add tables, analysis results. You have other outputs, then in that story stiffness. So you get the story stiffness table. It is directly available as stiffness output, but we want to know the ratios to check it. So usually we take it to the Excel by exporting it using the file export table to Excel option. And that will be, so you'll get this table. Then you have these for the X direction and Y direction in your static cases. And then the stiffness values are available, and we'll put a ratio here and ensure that it is greater than 1 to do this. So in this case, all the stories are fine. There is no soft story. So that is the output for soft story available in the program. Just need to extract the results to the Excel and do the ratio check. And then other irregularities such as mass irregularity. You can see this particular picture depicts it, and that can be found in two outputs. One is by creating a mass source combination and getting the output for it as story force. Like this, I created a seismic weight combination using those factors using the mass source, and then you'll get the output. Seismic weight, just to show you that this is one of the way. Whatever values used in the mass source definition, create a combination and use that combination output for story force. And filter it again and you'll get this. So I exported this to the Excel again, and I calculated the individual story weight, and then one ratio for the above, one ratio for the below. So any of these is greater than 1.5 can be checked quickly using this output. The other option is directly checking the mass. Mass is also available under model definition, other definitions, mass data as mass summary by stories. You can also use this to do the same calculation, except that this is the mass and the other one is the weight. So you can perform the check. Other thing related to the geometry that is to be checked externally. But if you want to model, of course, you can always model and check the scenarios or the severities arising from different types of analysis. Right. Strength irregularity or the big story. This is not covered in today's session. This requires a strength estimation, which requires a nonlinear analysis to estimate the strength of the members at each story level. Then that can be estimated, but it is completely doable in the ETABS program. Floating columns is not a desired item, but should be avoided in the lateral load resting system. So it is possible to model the floating columns. This will be in another discussion where we need to do some nonlinear analysis. So I'm keeping it for a future session. So I'm skipping it for now. And then you have the seventh item in that, which is irregular modes of oscillation in the two principal plan directions. So we have the output. In this model, again, we are going back to the same outputs, but this time under the structure, it will be model information. And we'll pick up the model participating mass ratios. And we can find one. There are two components. One is the first three transformation modes contribute less than, it has to be more than 65% that we can get it. So you need to identify the mass participating ratios from each node and the direction so that you can do a summation program. It gives a simple output where it sums up the cumulative values of the mass ratios here, which we typically do for any structure as a basic check. Here you can see the 98%, 99% in the X and Y direction, which is good enough. But for these specific irregularities, you need to check. You can take it to the Excel, and you can also make some conditional formatting to know the ranking or the first three modes in that particular direction based on the ratios. But you can see the first one, second one. Sorry, the second one is more on the torsion. This building is having significant torsion. Just wanted to show a real building where this kind of situation is rising. So you'll have to skip this one, this particular mode in the summation. So this is 1, and this is 2, and this 3. This is about 55 and 10. It's just about 65%. The other one is in y direction. So this is mode 3, mode 4. So it is already 70%. Right. So this small additional exercise you'll have to do, because modes are arbitrary depending on the number of modes. If local modes are dominating, here you can see in this case, you can see the periods are pretty close to each other, that these are the local modes that are existing in the structure. You can see some of the local modes dominating. Just to demonstrate, so these are structural mode, and you can see torsional along with the UX X1. This is torsional actually in this building, and then this is in y direction translation. And then if you go to the fourth mode, you see this. So this is called the local mode in the structure dominating here. Most likely the loading or the stiffness available there for the cantilever is not sufficient. So these are all the iterations that we'll do to bring in stiffness for the structure. Now coming back to this, this is how we ensure this 65% in the first 3 modes in that particular direction. So you can do this. So this is how vertical irregularities for the irregular modes can be checked. Now, just a quick summary of those items specific for irregularity checks. Modes and soft story are shown here. And finally, for the load combinations, for the design, you have the default combos. So we have the lateral loads in X and Y directions are covered under the auto or the default combinations. The vertical shaking, respect to Z, what we defined, when it is used, then you'll have to use the user-defined combinations. User-defined combination is always possible. In any case, you can define your own combination like this. And it is not necessary to add the signs for the spectrum case results, because internally the program will generate 8 subcombinations for permutation of the signs, and the envelope of it will be always used. So putting sign is not relevant for spectrum mode involved combinations. And that's all I wanted to present in this session.